Hello everyone, welcome to our webinar on interactive molecular space exploration with AI. My name is Miroslav Žičas and I am CTO from DeepMedChem. And in today's presentation, I would like to introduce a little bit our new application called Cheese Explorer, which is able to visualize chemical spaces. And then I would like to dive a little bit into the background. How does this technology compare to existing methods of chemical plotting? And how are we able to leverage our 3D shape and electrostatic representations to handle vast chemical spaces? Cheese Explorer is available on explorer.deepmedchem.com. You can access the website, and it's featuring 11 chemical databases visible in the legend, 4 representations: electrostatic, shape, fingerprint, and activity. From each database, there is around 100k data points, and it's both in 2D and in 3D. The databases available are visible in this summary table. There are both enumerative and combinatorial ones. For instance, Campbell is enumerative, while Explore, Cambria, and so on are combinatorial. And those databases have multiple types and are capturing different chemotypes. And for instance, some databases are focusing on medicinal chemistry and mainly drug-like molecules, while another have as well biologicals or even synthetic molecules. Another databases such as Coconut or FoodDB are containing natural products which are useful in food additives or fragrances. Here are logos of the databases. And now I would like to showcase the application in a few minutes. And if you want to join me, you can go to explore.deepmedchem.com, and here you have the controls how to navigate in the interactive plot. Let me share the screen. Now I am in the Explorer, and by default I see Campbell database, and I can hover over the molecules, and I see what the points are representing. By zooming and dragging, I can select some cluster and look into the molecules, what the cluster contains. And I can as well download the CSV. And by double clicking, I get back to the default view. I can move side to side and upside down like this. And by clicking on the legend, I am able to select multiple databases and display them over each other. So in this way, it's possible to observe how do the databases overlap, what are their commonalities and differences, where are the main clusters, and how the distribution of the databases look like. By double-clicking, I can isolate some database. For instance, here we have FoodDB. And I am able as well to color the databases by some property. So let's, for instance, look at molecular weight. Yeah, here we have molecular weight of FoodDB. And you can see that this database contains quite heavy compounds, and there is this interesting like cluster of large chains. While other databases, such as Campbell, have relatively small compounds in terms of molecular weight. And some databases, such as Cambria, are somewhere in the middle. That here, if I isolate, let me isolate Cambria, you can see most of them are in this range of around 500, 400. There are as well different properties. Now I selected number of aromatic rings. For instance, GDP17 has most of molecules with one or two. That's because it has maximum 17 atoms, so those are relatively small molecules with one or two rings maximum. And let me get back to the databases. I can visualize those databases not only in this default electrostatic mode, but as well in 3D shape similarity. So by selecting the shape here in the menu, those molecules should be now rearranged by shape similarity. We can test it by hovering over whether the molecules are shape similar, or selecting some cluster. Let me, for instance, try this one. And we can see that, most of these molecules have some shape similarities. Then there is representation based on traditional fingerprints. And finally, our new metric, which is trained on activities. So here it should represent activity similarities, and molecules close to each other should have high probability of being active on the same target. I can switch as well to 3D. And here I can interact with the same plot, but in full 3 dimensions, which might be useful in some cases where the clusters are overlapping. But in 3D, we have 1 dimension more, so there are more those intricacies captured. There are some premium features which will be available soon. One of them is visualizing custom molecules. So in future, you should be able to drag and drop your own molecules and visualize them easily in this UI on the top of the existing databases. And I see there are already questions appearing on like how does it work, if it's PCA or TSNE or UMAP, or what is on the x-axis and y-axis. And I will soon get into the technicalities and dive a little bit diver. This is just a showcase to see how it looks like. Here, if you are lost in the app, you have the tutorial and the table of chemical spaces that and references as I was showing in the presentation. If you are interested, you can log in and try the Pro version to get a higher resolution of the chemical spaces and be ready for the new features as they come. Now I will get back to our presentation. First of all, I would like to introduce existing approaches of molecular visualization and what are the existing methods. The most common way how to plot molecules is to visualize them by property. For instance, plot a molecular weight of the compounds on the x-axis and LogP on the y-axis. Then there are approaches to visualize chemical spaces hierarchically in terms of the most frequent scaffolds or most frequent chemotypes, rings or reactants. And then there is a family of dimensionality reduction methods which work by computing some descriptors. Traditionally, those are molecular fingerprints, and then reducing the dimensionality from 500 or 1000 dimensions to 2 dimensions, which will produce a nicely looking plot, which is capturing some commonalities in terms of proximity of the descriptors. For instance, similar fingerprints will be close to each other if you plot your molecules in this way. One of the most famous methods how to visualize chemical spaces is from a paper exploring chemical space for drug discovery using the Chemical Universe database from Raymond Group, which uses MQN, and these are quantum descriptors or other molecular descriptors such as heavy atom count, topology, number of rings, which are then visualized in 2D or 3D, and from these plots you get the distribution of various kinds of compounds, whether they are aromatic, heterocyclic, or what properties do they have, how much atoms do they have, how much H-bond acceptor, atom fraction, etc. Then you can annotate these plots, and it's used as well to analyze how big portion of all possible molecules are available in the existing databases. So then we can, for instance, enumerate the molecules which do not yet exist. Then this is an example of the hierarchical visualization. These are scaffold keys from Peter Ertl, and there is an interactive hub where you can browse a database based on the scaffolds contained. Recently, there was introduced a method called TMAP, which uses scaffold trees to visualize high dimensional datasets. And there are as well datasets of molecules visualized. Spanning trees, that's a type of graph or network, and we can construct the network in the high dimensional space and then plot it in 2D like this. And it's a one big spanning tree, if I'm not mistaken. In Explorer, we are using UMAP, and UMAP stands for Uniform Manifold Approximation and Projection, and we choose UMAP because it preserves the global and local structure as well of the high-dimensional neighborhood, and it's reproducible and interpretable. In contrast to T-SNE, it doesn't have the stochastic element in the same way, and thanks to that, we can reproduce the plots. I'm not sure if here the GIF is visible, but it should show the principle of how UMAP works. Maybe let me show the screen to show the animation. I'm not able to find it. So the animation here should demonstrate that if you have points like this and you construct a proximity graph that is connecting the nearest neighbors from all these data points, you will obtain some kind of skeleton or network, and then you can take this network and make a visualization in 2D to reduce the dimensions. Here is another example. Imagine we have some high-dimensional data. Here we see this mammoth, and we want to project it in 2D. And UMAP takes this high-dimensional manifold and tries to capture the topology in a way to preserve both the global and local structure. So you can imagine it as a mathematical way of capturing skeleton of high-dimensional data and then projecting it into a 2D. This method has its challenges because while linear algebra techniques such as principal component analysis scales very well, methods like spectral embeddings, T-SNE, or even UMAP are not so good in scaling to bigger number of data points. Here from this figure, it seems that with UMAP we will get reasonable speed in thousands or tens of thousands of points. But if you scale more to hundreds of thousands or millions, it's not longer possible to compute such visualization and have it in reasonable time with reasonable computational resources, because it doesn't scale linearly. So this is the main challenge of dimensional reduction plots, how to scale them. Another challenges are how to interpret the plot and what does it exactly capture, and how to handle multiple data sets and databases, because if you have a single data set, that's simple, but then how to add more data points, or how to create some UMAP visualizer to which you can add any database, and it will still make sense. Regarding scalability, we solve this issue by paradigm fit small and transform big, where to fit the UMAP model, we are taking 100K data point samples from multiple databases. The goal in this stage is to take as many databases as possible and have the training set as diverse as possible to capture the whole chemical diversity that you could encounter in existing chemical spaces. And after training on those database samples, we are able to transform any other molecule or any other database into this visualization. So the scalability bottleneck is really just in this stage of fitting the UMAP model. But after this stage, we are able to visualize as many data points as we want. To tackle the issue of interpretability, we rely on a method of creating isometric embeddings, which are being used as well across our products, such as cheese search for searching molecules, or modeler for training ADME predictors on those representations. And here is a sketch on how this method works, or what does it mean to be isometric. At first, you have pairs of molecules with some pre-computed 3D shape or electrostatic similarity, which is obtained by sampling conformers, aligning the conformers, and then computing electrostatics and evaluating 3D shape and electrostatic integrals to obtain the overlap and thus shape or electrostatic similarity of those molecules. And then our AI models are trained to preserve those relations in their latent space. So the AI models are producing high-dimensional Euclidean vectors, and in these Euclidean vectors, there are captured the ground truth similarities of the molecules. It's not ground truth, there is some margin of error, but it's proportionally. So if you have 0.9 shape similar molecules, it will translate into 0.1 Euclidean distance in the of the high dimensional vectors. After training such models, which are producing isometric embeddings, we are then working with a vector space where each compound is one vector. And with this vector space, we can structure the databases based on similarity. For instance, here we have 5.5 billion molecule database called enamine, and we are visualizing a sample from it of those similarity clusters. Based on it, then it's possible to search super fast or do virtual screening super fast, because you can just retrieve the nearest cluster and then search through the cluster to retrieve the nearest vectors. If you are interested in it, you can try it on cheese.deepmedchem.com. There is the search available. We are supporting billion scale databases, and you can do screens both in 3D shape, electrostatic similarities using those isometric embeddings. And to answer the question, what tools are used behind the 3D shape and electrostatic similarity, we are using SPSIM and ShapeSIM metrics from this paper on the value of using 3D shape and electrostatic similarities, which work by sampling conformers of molecules and then integrating over the volume overlaps and electrostatic fields. For the electrostatics, you can use either gas-staggered charges or another techniques, and we have our own AI models which are trained on like DFT quality data to obtain high accuracy electrostatic surfaces. These embeddings are novel in their speed accuracy trade-off, which is unprecedented in comparison of existing tools. There are both as accurate or even more accurate methods than cheese, which are doing 3D shape similarity screens, or even docking methods, let's say. And then there are methods as fast as cheese, but lacking the accuracy of these computationally heavy approaches. For instance, the computation time to search in 5.5 billion molecules is a few seconds with cheese, but with traditional 3D 3D screening methods, you would need years. Even 56 years with ROCs to compute on one CPU the similarities to molecules in the database and get the most shape similar ones. Next steps of this approach is to be able to visualize even more data points, and maybe that could be achieved by creating some sort of chemical space map. As an inspiration, I take Google Earth, where you can visualize the Earth and zoom in to the level of cities or streets to see all the details. And in a similar way, there could be a zoomable way how to visualize not only 100k data point samples, but even millions or billions of those molecules, and zoom in to see them all. As well, we are planning to support more databases. There are already new versions being prepared and more databases coming in. And if you have your favorite database, which is not yet available in our tools, you can write me or write us, and I would be glad to integrate it so it's visible in this visualization as well. If you are interested, we as well offer API access and on-premises solutions to all our tools. So it's possible to run them in your company and having your own databases in it. Thanks for your attention. That's all for today, and now there is space for questions. I would go through the comments, so you can ask in the comment section. There are some questions which I have already answered. One of those questions, what's the technique used? The answer is we are using UMAP. Another question, when extracting, analyzing, and visualizing data from public databases like Campbell and PubChem, do you perform any internal data curation, such as removing duplicate entries, stripping salts and fragments, neutralizing charges, etc., or do you use the data in its original form? Good question. We are using the data in the original form. We are canonicalizing the molecules to have them in canonical Smythe format, and everything which is a canonical, canonicalized molecule is then passes, and we work with that. Regarding duplicates, yes, duplicates are handled, and stripping salts, fragments, and charges and handling isomers such as tautomers or stereoisomers. That's then handled in the next step. If you search by our tools or use them in prediction, you can like filter out what you don't want. Usually salts are stripped automatically, but it depends. For instance, in this explorer, there is like everything that passed as a canonicalizable molecule. How do you deal with stochastic nature of UMAP? In contrast to Disney, where the S stands for stochastic, UMAP is not stochastic in the similar way that it would be like random, even if you run the exact same data with the exact same parameters. And there is some reproducibility in it as well. We are then able to add more data points, and the addition of more data points is not random. If you take a new molecule and visualize it on the top of existing ones, it will not be placed randomly, but based on the UMAP model. Is the full cheese workflow available? This workflow for visualization is not available like in terms of code, but it's available in the web app for free. You can use it as you want, and in our on-prem version there is a possibility to work with like all parts of the workflow and export the isometric representations and do whatever you want to do with them. So the workflow is customizable, and you can write us if you are interested in the version where it is. Then there is a question if we are able to cluster any properties such as lipophilicity, or if it's abstract high-dimensional similarity. That's a very good question. Our models are trainable on any sort of similarity. For us, and in this way, we train the models for electrostatic, 3D shape similarity, or even activity similarity. And as well, you could train a model in this way for lipophilicity similarity, which would put together isometrically molecules with similar lipophicilities. Is it abstract high-dimensional similarity? Well, it's not abstract. It's not abstract because it corresponds to those electrostatic similarities of the molecules and preserves the metric in this high-dimensional space. And in the space of in the chemical space arranged based on electrostatic similarity, it will already capture a lot of properties which are which depend on electrostatics. So it would be interesting to take the plot, color it by some properties such as LogP, lipophicility, or another ones, and try to see whether there is some like trend of how the latent space is organized, and whether similar electrostatics or similar shape corresponds to similar lipophicility or any other property. Thanks for these nice questions. If there is any more any question, I will give you last few minutes, and you can comment with your questions in the comment section. Okay, I don't see any new questions coming in. And in that case, thank you all for your attention. Feel free to get in touch with us. Here you see our emails. You can as well write on our company email, info@deepmedchem.com. You can access most of our tools for free on web. And if you are interested in more features, you can write us. We are glad to answer or even showcase for your team what features do our products have, and if there is a mutual fit. Yeah, one more question. Last one. Have you explored the sensitivity to conformer generation in the 3D electrostatic measurements? Yeah, the 3D shape similarity is sensitive a lot on how do you generate conformers, and because if you generate some conformers and then compute similarities rigidly by rigid alignment, it's possible that you would get low shape similarity. But if you rotate some bonds, then it would be shape similar. So this is certainly an issue, and we are trying to solve this by sampling more conformers. So for every molecule, we are sampling like 20 or 30 or even 100 conformers, and then aligning them all with each other in a way so that for each pair of molecule, there is the best aligned pair, which is then taken for the similarity, for the shape similarity computation. In the electrostatic mode, the alignment also takes into account the electrostatic charges to align properly based on it. Thanks for this question. Thank you again for listening today to our webinar. Contact us on our emails or on LinkedIn if you have any user feedback from the usage or new feature suggestions, or if you, especially if you are like interested in trying some of our products, feel free to contact us, and we are here glad to help. Thanks everyone, and have a nice day.